I have the first term being multiplied by the second term divided by a third term. So we're going to get 3 logs out of that. The first one, I'm going to be able to bring this 4 out front, right? So I'm going to get 4 natural log of x cubed minus 1 plus, because it's in the numerator, the second term, this has an exponent of 1/2. So I can bring the 1/2 out front, and I'll get natural log of 3x minus 1. And in the denominator means we subtract, so I'll get minus natural log of x squared plus 4. Then, if I take the derivative of both sides, the right-hand side is going to be easy to do, and it's explicit. Only the left-hand side is implicit. Okay, so here's what we're taking the derivative of. On the left-hand side, the derivative of natural log of y would be 1 over y times what? dy dx. On the right-hand side, the derivative of 4 natural log of x cubed minus 1 would be 4 over x cubed minus 1 times the derivative of the inside. What's the derivative of x cubed minus 1? 3x squared plus 1/2 times 1 over 3x minus 1 times the derivative of the inside. That's a chain rule. So times 3, and then we have minus 1 over x squared plus 4 times the derivative of the inside is 2x. So I'm going to get dy dx equals y times, so I'm multiplying both sides by this y here. If I clean this term up, I'm going to multiply those together. We get 12x squared over x cubed minus 1 plus 3 over 2 times 3x minus 1. And I could distribute that too, but there's no real reason to do it. Minus 2x over x squared plus 4. But I'm not done. When I started this problem, I did not have an implicit equation. I had an explicit equation. Therefore, my derivative needs to be explicit. So what we're going to do is put what y equals back in for our y here. So if I replace, yes, I can go back. So if I replace that y with what it is originally defined as, that will give me my final answer. And I don't need to go any further. Nothing simplifies, nothing cancels out. But since I started with explicit, I need to finish with explicit. But you can see how doing logarithmic differentiation allowed me to truly simplify these problems, because otherwise we would have been taking the derivative of this term right here. And that is a chain rule inside of a product rule with another chain rule as part of the product and a quotient rule. That would have been way more complicated. Now, I could have done that without logarithmic differentiation, but I really wouldn't want to. Let's look at another example. With this problem, I have no choice but to use logarithmic. Okay? Y equals x raised to the 2x. When you have a function of x raised to a function of x, we don't have any derivative rules for taking the derivative of that. But if I take the log of both sides, I can bring the exponent out front, and then we have something I know how to take the derivative of. So, I'm going to take the derivative of the left-hand side. I get natural log of y. On the right-hand side, I get natural log of x to the 2x. And the power property tells me I can bring that exponent out front. So this is really going to be 2x times the natural log of x. I haven't done any calculus yet. All I've done is take the log of both sides. So now we're going to ddx both sides of this. We're going to take the derivative of natural log of y. We're going to take the derivative of 2x natural log of x, which will be a product rule. On the left-hand side, the derivative of natural log of y is 1 over y times dy dx. On the right-hand side, so we're going to have derivative of the first times the second, so I'll have 2 natural log of x plus the derivative of the first times the derivative of the second. Derivative of natural log of x is 1 over x. So I get 1 over y dy dx equals 2 natural log of x plus 2, because these x's simplify and go to 1. Multiply both sides by y. And we can't leave the y there because my initial equation is explicit. I need my answer to be explicit. So we replace the y with the x to the 2x. And that is my answer.